Let's take a look at some more volumes of solids of revolution. So just as a reminder, I have projected again on the screen just our process for finding the volume of a solid of revolution by determining whether a cross-sectional slice is either a disk or a washer, and then setting up the area of that cross-section function by identifying the radius or radii, if there are more than one radius for the washers, and determining if we are going to be integrating with respect to x or with respect to y by whether the cross-sectional thickness is a delta x or a delta y. So we get that all set up, then we integrate and find the actual value of the volume. So again, these are just reiterating the formulas that we had already looked at. If we've got a disk, it's going to look something like that. And if we've got a washer, it's going to look something like that. We're going to determine if we are integrating with respect to x or y based on the thickness of our cross-sectional pieces, where we're cutting those cross-sections perpendicular to the axis of revolution. All right, so let's take a look at an example. All right, so let's take this particular problem. We want to find the volume of a solid formed by revolving the region that is bounded by y equals 2 sine of x, so a sine curve with an amplitude of 2, y equals 0, so that's the x-axis, on the bounded region from 0 to pi, and we want to do it around the horizontal line y equals -2. So let's get this graphed and take a look at what this looks like. So I set up my scale here. It's the sine curve. It has an amplitude of 2, and it will, on that region from 0 to pi, look like that. Now, of course, that keeps going, but we don't need the rest of it because we're looking at it just from 0 to pi. Then we're bounding it by the line y equals 0, so that's the x-axis. So I'm drawing it in there even though it's right on top of the x-axis. And this is the region. Let's go ahead and just highlight actually instead of dashing it out. This is the region that we are going to revolve. So it's going to be kind of that little sine, little bubble of the sine, and we're going to revolve that about, create a solid by revolving that about the horizontal line y equals -2. So y equals -2, I'm going to go ahead, I'll just dash this one in, could have drawn it solid, but that's the axis of revolution, and we're going to take this region and we're going to revolve it around that axis of revolution. So this is the axis of revolution, y equals -2. And we'll go ahead and write on here too. This was y equals 2 sine of x. Okay, so what would that look like? So let's think about drawing the solid. So once we've got the region, then we want to visualize the solid so we can see what the cross-sectional slices are going to look like. So this is going to get kind of big here. Yeah, so I am going to go ahead and make my scale a little bit smaller. We'll get that scale set up. Okay, so I got my scale set up, and let's see what this looks like. So this, let's take our region. So our region is right here. And we're going to revolve it around, now to kind of dash out that lower base. So that's the region. We're going to revolve it. So think of it coming out towards the viewer, coming out towards you out of the screen, and revolving 360 degrees around this line y equals -2. So we end up getting a reflection of that, essentially, mirrored across that axis of revolution. So we've got this region here, and this goes all the way around, so it's, it's scooping out. It's kind of hard to visualize three-dimensional from our two-dimensional screen, but think of that going all the way around, all the way around. And we could actually, this is like an interesting solid because we can actually stick our hand all the way through it. So it's got this, solid piece up here and the solid piece down here, which has gone all the way around. So it's solid all the way around, but we could stick our arm straight through it. There's a big hole. If you could see me, I'm, arrow indicating an arrow. Like you could stick your arm straight through this solid. But this solid has come around. It's filling in here and then around on the back side too, but it does have that hole in the center. So we've kind of got that shape. I'm going to draw one more little curve. Here, let me grab my black pen. I'm going to get a visual of what this thing looks like. Sometimes it can be hard to see what they look like. Okay, so I was going to put one more kind of thinking about it like coming out towards us like that. Okay, so that's what it looks like. Now we got to think about what would a cross-sectional slice look like. So a cross-sectional slice, I'm going to grab one of my little swoops I did here to indicate the curve coming out of the screen towards us. If I take a cross-sectional slice, I'm going to slice perpendicular to that axis of revolution. So I'm taking my knife and I'm slicing perpendicular to this axis of revolution. And it's going to come all the way around like that. And it's going to have, I'm not going to do dash lines. I'm just going to go ahead and do them all solid. But it's definitely going to be a washer. So you can see that washer right in there. It's definitely going to be a washer with a thickness of delta Y. So now we just have to figure out how to set up the area of that washer. So let's take a look at that washer as it relates to the original region and determine the inner and the outer radius. So I'm going to pull this out. We've got a washer. It's going to look something like that. And we've got our axis of revolution coming in right through there. And what we need to calculate is the inner radius. What we need to set up, I should say, is the inner radius and the outer radius, because the area of a washer, so we know that the thickness of our slices here are delta x, so we're going to have a function for the area that is going to be pi times the outer radius squared minus the inner radius squared. And then we'll plug that into our integral to compute the volume once we've come up with what this looks like and got it simplified. So a of x is going to be equal to pi times, well, how would we calculate the outer radius? So I'll go back to my picture up here. My outer radius, remember, comes from the axis of revolution to the outer part of the solid. So the outer part of the solid is all the way up to that function, y equals 2 sine of x. And so this length right here is the outer radius. Now, of course, like, over here for the washer right here, it would be that length and so forth. So the outer radius is going to be 2 sine of x, the top of that line right there, minus the bottom, right? So that's a negative 2. So we've got 2 sine of x minus a negative 2. So the outer radius is 2 sine of x plus 2. This length, by the way, is always a constant 2, and so that you're seeing that plus 2 coming into the radius right there. So that is the outer radius. Now, how would we calculate the inner radius? Well, let's think about it. The inner radius is this length right here of the washer. And so notice over here, I'm going to try to draw one more washer in my picture. Notice over here when we draw the washer, notice that the inner radius, the outer radius is changing, but notice that the inner radius is not changing. The inner radius for every slice is this length right here. So it's from here to here. It's this length. When we drew that one over here, the inner radius would be this length. Over here, the inner radius would be this length. They are the same length. The inner radius, regardless of where we take the slice, the inner radius is actually 2. Now, how could we see that? Well, that's because the function on the top is actually that line y equals 0. So I'll write it just so it's consistent with how we did the other one. The function on the top defining the radius is 0, and then we're subtracting the line, the axis of revolution down there, negative 2. So it's 0 minus a negative 2, which of course is just 2. But you can see visually from the graph that the inner radius is that constant 2 throughout all of the slicing and calculation of these areas of the washers. So the outer radius is, we're going to plug that into our formula, 2 sine of x plus 2 quantity squared. The inner radius is 2, so we square that. And I do like to get this all simplified. We're going to pop this into an integral here in just a second. But just so we don't have to simplify it in the integral, let's expand out that square. So 2 sine of x plus 2 squared is 4 sine squared of x plus 8 sine of x plus 4, and then we're subtracting 4. All right, and if we keep simplifying, oh, look at that, that's kind of nice. Keep simplifying a little bit, so this becomes pi times 4 sine squared of x plus 8 sine of x. and that is the area of a washer. So that is the area of the cross-sectional slice, which was a washer. All right, now we have everything we need to go ahead and put it into our volume. So to calculate the volume, I'm going to come over here where I have some more space. The volume of this solid. Now remember, the solid was defined from 0 to pi on the x-axis. So we're going from 0 to pi. You can see that within the solid, but you can also see that around the region that we revolved. So we're going to be integrating from 0 to pi the area of these washers with respect to x. So we're going to end up with the integral from 0 to pi, since we already did the simplification of the area function. It's going to be pi times 4 sine squared of x plus 8 sine of x dx. And here we get into some integration work. Now, one of the things I want to notice is that right here, that's just a basic integral. But this is not a basic integral. We don't know what the integral of sine squared is. And if we tried to do like a u sub or something like that on that, if I try to u sub, my du would be the cosine of x dx. So that's not going to work either because I don't have a cosine on that piece of the integral. And so I have to lean in a little bit to, let's put a little star. This one has a little subtle recall here. Let's recall that there is actually a trig identity that we can apply here. The sine squared of x, we can use the fact that the sine squared of x is 1 minus the cosine of 2x over 2. That is my half angle, one of my half angle formulas, or identities, I should say, not formulas. It's an identity. And, you know, it may have been a while since we've worked with them, but we're headed into here after we get done with chapter 6, we're going to head into just integration strategies. And one of the integration strategies, and I really do kind of group it with the basic integral strategies, is utilizing algebra or trig basics to simplify before we integrate. And right there, boom, we can look at that and say, oh, I can't integrate sine squared, but I will be able to integrate 1 minus the cosine of 2x over 2. So we'll make that substitution. So if you see a sine squared, or for that matter, if you see a cosine squared, you can use your trig identities to reduce them down to their equivalencies. So this is integral from 0 to pi. I'm going to go ahead and put in that identity now. 4 times 1 minus the cosine of 2x over 2. We'll integrate all at the same time, so I'll just carry that term down. I actually want to simplify one more line because this nicely reduces. So this becomes pi times integral from 0 to pi of 2 minus 2 cosine of 2x plus 8 sine of x. Now we can integrate. Each of these is just using our basic integration formulas. So we'll go ahead, we'll integrate this, plug in the bounds, and I'm going to go ahead and just speed up the video through that part a little bit. But this at this point is just using our basic integration formulas, and then we'll plug in those bounds and see what we get for our volume. And there it is. So we have 2 pi squared plus 16. Oh, that should be 16 pi. I just caught my own little mistake right there at the end. I distributed the pi to both of those. So we should have 2 pi squared plus 16 pi units cubed of volume. And I didn't do the approximation for that, but we could pop that into a calculator and see what that is. But this one is, this one had a lot going on in this example. So, right, we're revolving around an axis other than the x or the y-axis. We're revolving around a horizontal line, so there's that shift off of the x or the y-axis, so we have to adjust for that when we're calculating our radii. And we have a washer, and within the midst of calculating our volume here, we had to apply a trig identity. So definitely one of the more challenging examples or problems that we've looked at in this section. But here we are at the end of this section and getting into these ones that are a little bit harder. But the process is always the same. So sketch the region, revolve it around the given axis, sketch the solid, determine if the cross-sectional slices are washers or discs, set up those area formulas, and then integrate across the appropriate bounds.